Look up at the night sky for long enough, and the stars begin to lie to you. They seem close. The moon feels like somewhere you could almost reach. Even the Milky Way looks like little more than a pale streak across the darkness, as if it were painted just above your head. But almost everything you are looking at is separated from you by distances so enormous that the numbers eventually stop feeling like numbers at all. The moon is far enough away that every planet in the solar system could fit, side by side, in the gap between us. The sunlight touching your window left the sun 8 minutes ago. The nearest stars are so distant that light itself needs years to cross the space between. And by the time we reach the faraway galaxies, a journey of billions of years becomes almost ordinary. So tonight, we're going to start somewhere familiar and slowly work our way outward until even the largest distances your mind can picture begin to feel strangely small. Welcome to the Snoozy Scientist. I'm very glad you're here. Before we go anywhere, I'd love to know where in the world you're watching from tonight. Pop it in the comments if you'd like. A city, a country, or even just bed is perfectly fine. It's always a quiet pleasure seeing how far this little channel has travelled. If these slow scientific wanderings help you relax, a like and subscribe is always enormously appreciated. It really does help this snoozy little corner of the universe keep growing. We have quite a long way to go, from the moon, past the planets, out to the nearest stars, across the Milky Way, and eventually toward the very edge of the observable universe. And somewhere along the way, the numbers are going to stop behaving like anything you can comfortably imagine. So let's begin with a deceptively simple question. How far away is everything in the universe? Get comfortable and let the scale grow slowly around you. Human beings are surprisingly good at judging distance, provided the distance is small enough. You can glance across a room and have a reasonable sense of whether something is 3 meters away or 10. You can look down a street and tell whether a person is nearby or several hundred meters into the distance. Even a journey of a few kilometers still feels like something the mind can hold quite comfortably. These are the scales we live inside. A typical room might be 4 or 5 meters across. A residential street might stretch for a few hundred meters. A walk through a town could cover several kilometers. Drive from one city to another, and perhaps the distance becomes 50, 100, or 200 kilometers. The numbers are getting larger, but they still mean something. If someone tells you that a shop is 2 kilometers away, you can roughly imagine the walk. If a city is 200 kilometers away, you may immediately think of a few hours in a car. Distance at this scale can be translated into experience. And that ability is more important than it first appears. The human brain did not develop while trying to visualize galaxies. For almost all of human history, useful distances involve things such as the other side of a field, the nearest water source, the next settlement, or perhaps the horizon. Our intuition was shaped by meters and kilometers. Earth itself is where that intuition begins to struggle. The planet beneath us has a diameter of roughly 12,700 kilometers. Measured around the equator, its circumference is close to 40,000 kilometers. 40,000 kilometers sounds large, but it is still just about imaginable, because humans routinely travel substantial fractions of it. A commercial aircraft flying at around 900 kilometers per hour could, in a simplified journey without stopping, cover 40,000 kilometers in roughly 44 hours. Walking would be rather less convenient. At a steady 5 kilometers per hour, without ever sleeping, eating, resting, encountering an ocean, or developing an understandable dislike of walking, travelling 40,000 kilometers would take around 8,000 hours. That is roughly 330 days of continuous movement. Realistically, of course, it would take far longer. Already something interesting is happening. Earth looks small in photographs. On a globe, you can hold the entire planet in your hands. But the real object is so large that ordinary human movement becomes a poor way of understanding it. Consider the distance through Earth itself. From one side of the planet directly through its centre to the other side is about 12,700 kilometres. A commercial aircraft could theoretically cover a comparable distance in around 14 hours if it could somehow fly in a perfectly straight line through the planet, which would raise several practical problems long before the refreshments trolley arrived. Yet there is something that crosses distances like these almost effortlessly. Light in a vacuum. Light travels at approximately 299,800 kilometres every second. That speed is so far beyond ordinary experience that even Earth suddenly becomes small. During a single second, light could travel a distance equivalent to going around Earth's equator roughly 7.5 times. Imagine beginning in London, travelling all the way around the planet, returning to London, and then doing it again. And again. And again. More than 7 complete circuits of Earth would fit into the distance light travels while 1 second passes. This is why light becomes such a useful ruler when thinking about the universe. Kilometres remain perfectly valid, but enormous distances eventually force us to write numbers containing so many zeros that the number becomes more difficult to understand rather than more informative. Scientists deal with this problem partly through scientific notation. The idea is simply to express very large or very small numbers compactly by describing their scale rather than repeatedly writing long strings of zeros. Astronomy also solves the problem by changing the ruler itself. Instead of describing every distance in kilometres, astronomers introduce units suited to the scale being measured. This happens because a useful unit should make a number easier to understand. Imagine describing the length of a country entirely in millimetres. Nothing would be scientifically wrong with doing so. It would simply be unnecessarily awkward. The same problem appears in space. Earth's diameter of around 12,700 kilometres is manageable. Earth's circumference of around 40,000 kilometres is manageable. Even a journey involving hundreds of thousands of kilometres can still be stated without too much difficulty. But eventually there will be millions of kilometres, then billions, then trillions, and even trillions will soon become inconveniently small. This is where our intuition begins to separate from the mathematics. There is an enormous difference between understanding a number and imagining it. Most of us understand what 1 billion means mathematically. It is 1,000 million. But forming an internal picture of 1 billion individual objects is much harder. Time provides a useful example. 1 million seconds lasts a little under 12 days. 1 billion seconds lasts almost 32 years. The words million and billion sound like neighbouring steps in a sequence, but the lived difference between them is enormous. Distance behaves in much the same way. The farther outward we measure, the more easily language can hide the actual increase in scale. 10,000 kilometres, 10 million kilometres, 10 billion kilometres. Each phrase is only slightly longer than the last, yet each describes a radically different amount of space. So Earth is useful as our first ruler. For the moment, 12,700 kilometres feels enormous. 40,000 kilometres around the planet feels enormous. A beam of light circling Earth more than 7 times every second feels almost absurdly fast. But the remarkable thing about astronomical distance is that none of these impressions lasts for very long. Earth will remain exactly the same size. Only our reference point will change, and as that reference point expands, an entire planet that once seemed impossibly large will gradually become little more than a tiny marker inside distances far beyond anything human intuition was ever built to understand. The moon feels close because we can see it so clearly. On a bright night, its craters and darker plains are visible even without a telescope. It hangs above us as though it belongs to the same immediate landscape as the clouds and the horizon. But the space between Earth and the moon is far larger than it appears. The average distance from the centre of Earth to the centre of the moon is approximately 384,400 kilometres. That is already almost 10 times the entire circumference of Earth, and for the first time, Earth itself becomes useful as a measuring stick. Our planet is roughly 12,700 kilometres wide. If we placed copies of Earth side by side across the average distance to the moon, we could fit roughly 30 Earth diameters into the gap. 30 entire Earths. That can be surprisingly difficult to reconcile with the familiar diagrams of the Earth and Moon, because those diagrams almost always compress the distance dramatically. If they showed Earth and the Moon at their correct relative sizes and separation, most of the picture would simply be empty space. Imagine shrinking Earth until it were about the size of a tennis ball. At that scale, the Moon would be roughly the size of a small marble. But you would not place that marble a few centimetres away. It would need to be almost 2 metres from the tennis ball. Suddenly, the Earth-Moon system looks less like two neighbouring objects and more like two tiny islands separated by a substantial empty gap. Human travel makes that emptiness even more apparent. Suppose a commercial aircraft could somehow leave Earth and fly directly toward the Moon at around 900 kilometers per hour. There would be no atmosphere to support it, of course, and aircraft are generally happier when air is involved. But we can ignore that detail for the comparison. Flying continuously at that speed would take roughly 18 days to reach the Moon. No stops. No sleep. No delays. Just more than 2 weeks of travelling at hundreds of kilometers per hour. Driving would take far longer. At 100 kilometers per hour, moving continuously day and night, the journey would require around 160 days. That is more than 5 months. And yet light crosses the same gap almost immediately. Light takes approximately 1.3 seconds to travel the average distance from the Moon to Earth. A little more than a single second. This is one of the first places where light becomes a wonderfully useful way of thinking about distance. Instead of saying 384,400 kilometers, we can think of the Moon as being about 1.3 light seconds away. When you look at the Moon, you are therefore not seeing it exactly as it is at that instant. You are seeing it as it was roughly 1.3 seconds earlier. The difference is tiny on human timescales, but the principle will become enormously important as the distances grow. We can also use that travel time to measure the Moon with remarkable precision. During the Apollo missions, astronauts placed special retroreflectors on the lunar surface. These devices are designed to return incoming light in approximately the direction from which it arrived. Observatories on Earth can fire extremely short laser pulses toward these reflectors. The pulse travels to the Moon, strikes the reflector, and a tiny fraction of the light returns to Earth, by measuring how long the complete round trip takes. Scientists can calculate the distance to the Moon with extraordinary accuracy. The entire journey there and back takes a little over 2.5 seconds. Modern lunar laser ranging measurements can determine the Earth-Moon separation to extraordinary precision, allowing researchers to study not only the Moon's orbit, but also subtle aspects of gravitational physics and the slow evolution of the Earth-Moon system. And the distance is not constant. The Moon does not travel around Earth in a perfect circle. Its orbit is elliptical. At perigee, when the Moon is closest to Earth, its centre can be roughly 363,000 kilometres away. At apogee, when it is farthest away, that distance can grow to roughly 405,000 kilometres. So the difference between the nearest and farthest parts of a typical lunar orbit is more than 40,000 kilometres. That variation alone is comparable to the entire circumference of Earth. This is an important feature of astronomical distances. Objects move. Orbits are often elliptical. Planets and moons do not remain at one fixed separation from one another, which means a single distance is frequently an average rather than a permanent value. Even so, the average Earth-Moon distance is useful because it gives us our first genuinely large stretch of nearby space. And perhaps the strangest part is how empty that stretch is. Earth occupies only a tiny portion of it. The Moon occupies even less. Almost everything between them is simply space. The gap is large enough to contain roughly 30 Earths from one end to the other, yet when we look upward, the Moon still feels like the object next door. For now, 384,000 kilometres seems enormous. A journey of months by road, more than 2 weeks at the speed of an airliner, about 1.3 seconds for light. But astronomical scale has an odd habit of making yesterday's enormous distance look very small. The Earth-Moon gap is the first great emptiness beyond our planet, and on the scale of the wider solar system, even this vast separation is only the beginning. The Moon may feel distant, but the Sun changes the scale completely. The average distance from Earth to the Sun is approximately 149,600,000 kilometres. That is nearly 400 times farther than the average distance from Earth to the Moon. The jump is so large that the Moon, which only moments ago seemed separated from us by a vast empty gulf, suddenly begins to look almost close. Imagine placing the Earth-Moon distance end to end, over and over again. You would need nearly 400 of those gaps before reaching the Sun. That is one of the recurring peculiarities of astronomical scale. A distance can feel enormous until a larger one arrives and quietly makes it look ordinary. 149,600,000 kilometres is still a perfectly valid way to describe the Earth-Sun distance, but astronomers soon realised that numbers like this become cumbersome when repeated across an entire planetary system. So astronomy uses a larger ruler. One astronomical unit is defined as exactly 149,597,870 kilometres. In practice, it is useful to think of one astronomical unit as roughly the average distance between Earth and the Sun. Once that unit exists, the solar system becomes much easier to describe. Earth orbits at roughly 1 astronomical unit from the Sun. Other planets can then be compared with Earth using the same scale, rather than continually reciting enormous numbers of kilometres. This is not changing the distance itself, it is simply changing the ruler. The same idea appears everywhere in measurement. We normally describe the distance between cities in kilometres rather than centimetres. Astronomers do something similar, except their inconvenience involves rather more zeros. Light provides another way of understanding the same gap. Sunlight takes roughly 8 minutes and 20 seconds to travel from the Sun to Earth. So when sunlight reaches your face on a clear day, you are not seeing the Sun exactly as it is at that instant. You are seeing it as it was a little over 8 minutes earlier. Compare that with the Moon. Moonlight takes only about 1.3 seconds to reach Earth. The Moon is therefore a little over 1 light second away, while the Sun is more than 8 light minutes away. The physical difference between those two distances is enormous, but light turns both into something that can be understood using time. This becomes increasingly useful because light travels at approximately 299,800 kilometers every second. At that speed, 150 million kilometers takes only a few minutes. Human transport tells a rather different story. Suppose a commercial aircraft could somehow fly directly toward the sun at around 900 kilometers per hour. Ignoring the absence of air, the heat, the fuel requirement, and several other fairly substantial inconveniences, the journey would take roughly 19 years. That would be 19 years of continuous flight. No landing, no stopping, no delays, no particularly welcome announcement from the captain that the destination was now visible ahead. A car travelling at 100 kilometers per hour would need well over 170 years to cover the same distance without stopping. Light manages it in just over 8 minutes. This contrast shows why the speed of light will become increasingly valuable as our reference point. It is fast enough to make the solar system feel manageable, while remaining slow enough on cosmic scales to reveal just how enormous the universe really is. For much of human history, however, even determining the Earth-Sun distance was extremely difficult. Astronomers could work out the relative arrangement of the planets long before they knew the true scale of the system. Johannes Kepler, using the exceptionally precise observations gathered by Tycho Brahe, developed his laws of planetary motion in the early 17th century. These laws described how planets orbit the Sun in ellipses and allowed astronomers to compare the sizes of different planetary orbits. They could say, in effect, that one orbit was several times larger than another. What remained difficult was determining how large the whole system was in kilometers. One important method involved transits of Venus. A transit occurs when Venus passes directly between Earth and the Sun, appearing as a small dark disk moving across the Sun's face. Edmund Halley recognized that observers at widely separated locations on Earth could time such a transit and use differences in the apparent path of Venus to help determine the scale of the solar system. The geometry depended upon parallax, the apparent shift in the position of an object when viewed from different locations. Transits in 1761 and 1769 became major international scientific events, with expeditions sent to distant parts of the world. The observations were difficult and imperfect, but they helped refine estimates of the Earth-Sun distance. Later methods became much more precise. Radar ranging allowed astronomers to transmit radio signals toward nearby planets and measure how long the reflected signals took to return. Because the speed of light is known so accurately, travel time can be converted into distance. Modern spacecraft tracking and planetary dynamics have refined the scale still further. The result is that a distance once extraordinarily difficult to determine is now known with remarkable precision. Yet knowing the number and picturing the number are still very different things. Suppose Earth were reduced to the size of a small peppercorn, only a few millimeters across. The Sun, scaled appropriately, would be roughly the size of a large exercise ball. But it would not be sitting conveniently beside the peppercorn. It would need to be placed tens of meters away. The empty space between them would dominate the model. This is one reason illustrations of the solar system are almost always deceptive. If the planets are drawn large enough to see clearly, their distances usually have to be compressed. If their distances are drawn accurately, the planets become tiny and most of the image becomes blank space. The real solar system contains far more emptiness than familiar diagrams suggest. For now, 150 million kilometers feels vast. It takes light more than 8 minutes to cross. It would take an aircraft almost 2 decades, and nearly 400 Earth-Moon distances could fit into the gap. But 1 astronomical unit is still only the beginning of the solar system. The outer planets lie several, then tens, of astronomical units from the Sun. Very soon, even the enormous Earth-Sun distance will become something we casually use as a measuring stick. Once the distance between Earth and the Sun becomes familiar, the rest of the solar system begins to reveal just how misleading those neat little rows of planets can be. Mars is the first good example. Its average distance from the Sun is roughly 228 million kilometers, or about 1.5 astronomical units. But Mars is not always the same distance from Earth, because both planets are moving around the Sun on different orbits. When Earth and Mars are relatively close on the same side of the Sun, the gap between them can shrink to well under 100 million kilometers. At other times, when the planets are on opposite sides of the Sun, they can be separated by several 100 million kilometers. So asking how far away Mars is does not have one permanent answer. The number changes continuously. That is true throughout the solar system. Planets are not fixed points sitting in a diagram. They are moving objects following elliptical orbits, which means the distance from Earth to another planet depends on where both worlds happen to be at that moment. Even so, their average distances from the Sun give us a useful way to understand the growing scale. Jupiter orbits at an average distance of roughly 778 million kilometers from the Sun. That is more than 5 astronomical units. The Earth-Sun distance that recently seemed enormous would need to be placed end to end more than 5 times to reach Jupiter's average orbit. Saturn is farther still. Its average distance from the Sun is roughly 1.4 billion kilometers. For the first time, billions of kilometers begin appearing naturally in the description. Saturn sits at around 9.5 astronomical units from the Sun, meaning its average orbital distance is almost 10 times the distance between Earth and the Sun, and even that is only the middle region of the planetary system. Uranus orbits at an average distance of roughly 2.9 billion kilometers from the Sun. That is about 19 astronomical units. Neptune, the most distant major planet, lies at an average distance of roughly 4.5 billion kilometers from the Sun, around 30 astronomical units. By this point, kilometers are still technically fine, but they are beginning to feel cumbersome. 4.5 billion kilometers is not especially graceful to repeat every time Neptune is mentioned. 30 astronomical units communicates the scale more cleanly. And light travel time gives us another way of feeling the expansion. Sunlight takes a little over 8 minutes to reach Earth. At Jupiter's average orbital distance, light takes roughly 43 minutes to travel from the Sun. At Saturn, the journey is around 1 hour and 20 minutes. At Uranus, sunlight takes roughly 2 hours and 40 minutes. By Neptune, light from the Sun needs a little over 4 hours to arrive. That means Neptune is more than 4 light hours from the Sun. This sounds manageable when expressed in hours, but the physical distance involved is enormous. Light can cross it during part of a day. Human spacecraft require years. Voyager 2 provides one of the clearest comparisons. The spacecraft launched in 1977 and eventually flew past all 4 giant outer planets. It reached Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. From launch to its encounter with Neptune, roughly 12 years had passed. Light covers the Sun-Neptune distance in a little over 4 hours. A spacecraft travelling at tens of thousands of kilometers per hour took more than a decade to make its way through the outer solar system. New Horizons gives another useful example. It launched in 2006 and travelled toward Pluto at extraordinary speed, reaching the dwarf planet in 2015. That journey still took more than 9 years. This difference between light and spacecraft becomes increasingly important as distances grow. A signal can cross the solar system far more quickly than a machine can. But even signals are no longer instantaneous. Robotic spacecraft communicate with Earth using radio waves, which travel at the speed of light. The National Aeronautics and Space Administration Deep Space Network uses large antennas around the world to send commands to spacecraft and receive scientific data from them. When a probe is close to Earth, the delay may be small. When it is near Mars, the one-way light travel time can vary from a few minutes to more than 20 minutes. A command sent from Earth cannot receive an immediate response, because the radio signal must first cross the interplanetary gap. If a spacecraft is 20 light-minutes away, the command requires 20 minutes to arrive. If the spacecraft responds immediately, that reply needs another 20 minutes to return. A simple exchange can therefore take 40 minutes. Near the distance of Neptune, a one-way signal can require several hours. There is no way to press a button on Earth and control a distant spacecraft in real time. By the time Earth receives confirmation of what happened, the spacecraft has already spent hours continuing on its own. This is a practical consequence of distance. The solar system is not just visually large, its scale affects how exploration works. And perhaps the most striking feature is still the emptiness. Pictures of the planets usually place them close together, because otherwise the image would be mostly blank. If the Sun and planets were displayed at the correct scale, the worlds themselves would occupy very little of the total space. There are enormous gaps between the planetary orbits. Earth is roughly 1 astronomical unit from the Sun. Mars lies at about 1.5. Jupiter is more than 5. Saturn is nearly 10. Uranus is around 19. Neptune is around 30. The farther outward we move, the larger the stretches of apparently empty space become. And yet Neptune does not mark the true end. Beyond it lies a vast population of smaller icy objects, including Pluto and the broader Kuiper belt. Farther still, the Sun's influence continues into regions that extend well beyond the planetary system. So 4.5 billion kilometers, 30 astronomical units and more than 4 light hours may sound like an extraordinary distance. They are. But they still describe only the region occupied by the major planets. The solar system continues far beyond Neptune, and the scale is about to expand again. Beyond Neptune, the solar system does not suddenly stop. There is no wall, no sharp line, and no point where a traveller would cross a perfectly defined boundary and leave everything belonging to the Sun behind. Instead, the solar system fades outward through several different regions, each with its own possible claim to being the edge. The first of these begins almost immediately beyond Neptune. The Kuiper belt is a broad region of icy bodies extending outward from roughly 30 astronomical units from the Sun. It contains Pluto, along with many smaller objects left over from the early formation of the solar system. Pluto itself orbits the Sun at an average distance of roughly 5.9 billion kilometers. That is close to 40 astronomical units. The Earth-Sun distance, which once seemed enormous, could therefore be placed end to end almost 40 times before reaching Pluto's average orbit. Light takes a little over 5 hours to travel from the Sun to Pluto at that average distance. A radio signal sent from Earth can therefore take several hours to reach a spacecraft operating that far away, depending upon the positions of Earth and Pluto at the time. Yet even Pluto is still surprisingly close compared with the outermost regions influenced by the Sun. The Kuiper belt extends much farther than the familiar planetary system, and beyond it lies an even larger structure defined not by solid objects, but by the Sun's interaction with surrounding space. The Sun constantly releases a stream of charged particles known as the solar wind. This flow expands outward in every direction, carrying the Sun's magnetic influence with it. Together, this creates a vast region known as the heliosphere. The heliosphere surrounds the planets and stretches far beyond Neptune. Eventually, however, the outward pressure of the solar wind weakens enough to encounter the material between the stars. That surrounding material is known as the interstellar medium. The boundary region where the solar wind can no longer expand freely against the interstellar environment is called the heliopause. This is one of the most useful definitions of the edge of the solar system, and humanity has actually sent spacecraft across it. Voyager 1 launched in 1977. After travelling outward for more than 3 decades, it crossed the heliopause in 2012 at a distance of roughly 121 astronomical units from the Sun. That made Voyager 1 the first human-made spacecraft to enter interstellar space in the specific sense of leaving the Sun's heliosphere. Voyager 2 later crossed the heliopause as well in 2018. The numbers involved are already extraordinary. 121 astronomical units is more than 18 billion kilometres. Light can cross that distance in roughly 17 hours. Voyager 1 required about 35 years to reach it. That contrast is a useful reminder of how enormous the difference is between the speed of light and the speed of even our most successful spacecraft. A distance that light crosses in less than a day required a machine built by humans to travel for decades, and the heliopause still does not necessarily represent the outermost extent of the solar system. The Sun's gravity reaches far beyond the heliosphere. This is where the Oort cloud enters the picture. The Oort cloud is a proposed vast reservoir of icy bodies surrounding the solar system at enormous distances, unlike the Kuiper belt, which has been observed directly through many individual objects. The Oort cloud has not been directly imaged as a complete structure. Its existence is inferred largely from the orbits of long-period comets that enter the inner solar system from extremely distant regions. Its exact dimensions are therefore uncertain. The inner Oort cloud may begin at distances of thousands of astronomical units from the Sun. The outer regions may extend to tens of thousands of astronomical units, and some estimates place the outer limit at around 100,000 astronomical units. At 100,000 astronomical units, the distance is roughly 1.5 light years. That is an astonishing change in scale. Neptune lies around 30 astronomical units from the Sun. Pluto averages about 40. Voyager 1 crossed the heliopause at roughly 121. And yet the Sun may remain gravitationally connected to objects tens of thousands of astronomical units farther out than that. The solar system, depending upon how it is defined, may therefore stretch vastly farther than the region occupied by its planets. This is why asking where the solar system ends does not produce one simple answer. If the solar system means the region of the major planets, then Neptune provides a convenient outer marker. If it means the zone populated by many icy bodies, then the Kuiper belt carries us farther. If it means the region dominated by the solar wind, then the heliopause provides another boundary. And if it means the outermost objects still gravitationally bound to the Sun, then the possible Oort cloud carries the edge much farther into space. Different definitions produce different distances because there is no single physical shell surrounding the Sun. The system fades into interstellar space. And this is where astronomical units begin to lose some of their convenience. 100 astronomical units is easy enough to say. 1,000 is still manageable. 10,000 begins to sound less intuitive. By the time distances approach 100,000 astronomical units, another unit begins to make more sense. The light year. A light year is the distance light travels in 1 year. Even an outer Oort cloud stretching roughly 1.5 light years from the Sun would not reach the nearest neighbouring star. Proxima Centauri lies more than 4 light years away. So imagine the entire planetary system, the Kuiper Belt, the heliosphere, Voyager 1, and perhaps even the enormous Oort cloud surrounding all of them. Then imagine that whole structure occupying only part of the distance to the next star. The solar system that seemed vast when Neptune was 4.5 billion kilometers away is already beginning to shrink. The ruler is changing again. And once distances are measured not in billions of kilometers or even thousands of astronomical units, but in years of travel for light itself, the scale of space begins to become something entirely different. There is a point where kilometers stop being helpful. Not because the kilometre becomes inaccurate, but because the numbers become so large that they begin to hide the distance rather than explain it. The nearest known star to the Sun provides that moment. Proxima Centauri lies roughly 4.24 light-years away. That sounds almost modest after travelling through billions of kilometres and thousands of astronomical units. 4.24 is a much smaller number than 5 billion. But the unit has changed completely. A light year is not a measurement of time, it is a measurement of distance. It is the distance light travels through a vacuum during 1 year. Light moves at approximately 299,800 kilometers every second. Allow it to continue at that speed for an entire year and it covers roughly 9.5 trillion kilometers. 1 light year is therefore close to 9.5 trillion kilometers. Proxima Centauri, at a little over 4 light years away, is separated from us by roughly 40 trillion kilometers. 40 trillion. This is why kilometers finally begin to collapse as a useful mental ruler. There is nothing incorrect about saying that Proxima Centauri is around 40 trillion kilometers away, but the number has become so large that it is difficult to attach any intuitive meaning to it. 4.24 light-years tells us something much more useful. It tells us that even light, the fastest thing allowed to carry information through empty space, requires more than 4 years to cross the gap. The sunlight reaching Earth takes around 8 minutes and 20 seconds. Light from Neptune's distance takes a little over 4 hours to reach the Sun. Light from Proxima Centauri requires more than 4 years. The jump from interplanetary space to interstellar space is enormous. Imagine Neptune's average distance from the Sun, roughly 4.5 billion kilometers. That once seemed almost impossibly large. But you would need to repeat a distance of that general scale thousands of times before approaching the distance to Proxima Centauri. Even the heliopause, crossed by Voyager 1 at roughly 121 astronomical units, sits comparatively close to the Sun. The possible Oort cloud may extend vastly farther, perhaps tens of thousands of astronomical units, and potentially around a light year or more in its outermost regions. Yet even that enormous structure would occupy only part of the gulf between the Sun and its nearest stellar neighbour. Proxima Centauri is close in astronomical terms. That is perhaps the strangest part. It is the nearest known star beyond the Sun, and yet it lies so far away that current spacecraft technology makes the distance almost absurd. Voyager 1 offers a useful comparison. Voyager 1 is not travelling toward Proxima Centauri, so it would be misleading to imagine it eventually arriving there. Its actual trajectory carries it in a different direction through interstellar space. but its speed can still be used as a reference. Voyager 1 moves relative to the Sun at roughly 17 kilometers per second. That is incredibly fast by ordinary standards. At that sort of speed, crossing a distance comparable to the gap between the Sun and Proxima Centauri would require on the order of 70,000 years. Not 70 years, not 700, tens of thousands of years. A civilization could rise, change beyond recognition, and disappear during the journey. Light completes the same crossing in just over 4 years. The distance is enormous enough that simply measuring it presented astronomers with a major historical challenge. Nearby stars appear fixed in the night sky, but they are not perfectly fixed. As Earth moves from one side of its orbit to the other, our viewpoint changes by nearly 300 million kilometers. A nearby star can therefore appear to shift very slightly against the much more distant background stars. This apparent movement is called stellar parallax. The basic idea is familiar. Hold one finger in front of your face and look at it with one eye closed. Then switch eyes. Your finger appears to move against the background. The finger has not actually jumped sideways. Your viewpoint has changed. Astronomers use the same geometric principle on an incomparably larger scale. Earth's orbit provides the changing viewpoint, and nearby stars provide the foreground objects. The difficulty is that the angles involved are extraordinarily small. For centuries, astronomers understood that stellar parallax should exist, but their instruments were not precise enough to measure it reliably. That changed in 1838. German astronomer Friedrich Wilhelm Bessel successfully measured the parallax of the star 61 Cygni. The result provided one of the first reliable direct measurements of the distance to another star. It also revealed just how enormous interstellar space truly was. Even the nearest stars were far more distant than the scale of the solar system. Modern astronomy has taken this method much further. The European Space Agency Gaia mission was designed to perform extraordinarily precise astrometry. Astrometry is the measurement of the positions and motions of objects in the sky. By repeatedly observing stars from different points along Earth's orbit, Gaia has measured tiny apparent shifts and built an extraordinarily detailed three-dimensional picture of our region of the Milky Way. For nearby stars, parallax can provide direct geometric distances. As the stars become farther away, however, the apparent shifts become smaller and smaller. Eventually, even parallax begins to reach its practical limits, just as kilometers and astronomical units reach theirs. The physical scale can be made clearer with a model. Suppose the entire orbit of Neptune was shrunk until it fitted comfortably inside a room. The Sun would be tiny. Earth's orbit would be smaller still. All of the planets would occupy a compact central region. Yet on the same scale, the next star would not be sitting just beyond the wall. It would be astonishingly far away compared with the planetary system itself. That emptiness is one of the defining features of interstellar space. Stars may appear crowded across the night sky because we see them projected onto a distant dome. In reality, enormous three-dimensional gaps separate them, and Proxima Centauri is merely the nearest example. 4.24 light-years is considered our immediate stellar neighbourhood. 40 trillion kilometres is, astronomically speaking, nearby. That single fact shows how dramatically the scale has changed. Earth once seemed large at 12,700 kilometres across. The Moon seemed distant at nearly 400,000 kilometres. The Sun transformed the scale at around 150 million kilometres. Neptune pushed it into billions. And now even trillions of kilometres have become inconvenient. From here, the light year is no longer an exotic unit. it becomes the ordinary ruler. Once the distance to the nearest star becomes familiar, something else begins to change. Proxima Centauri no longer feels like a lonely destination at the edge of everything. It becomes the first point in a much larger neighborhood. The Sun is surrounded by other stars in every direction, each separated from us by distances measured in light years. Some are only a little farther away than Proxima Centauri, others lie tens of light years from us. And once we begin thinking in spheres rather than simple straight lines, the amount of space involved grows very quickly. Start with a radius of 10 light years around the Sun. That region already contains dozens of known stellar systems. Alpha Centauri, the wider system that includes Proxima Centauri, lies just over 4 light years away. Barnard's star is roughly 6 light years from us. Sirius, the brightest star in Earth's night sky, is about 8.6 light years away. Each of these stars appears as a small point in the sky, but none is remotely close in ordinary terms. Even Sirius, which seems almost conspicuously bright, is separated from us by more than 80 trillion kilometers. Brightness does not tell us distance by itself. A star can appear bright because it is close, because it is intrinsically luminous, or because of some combination of the two. That is one reason the night sky can be deceptive. When we look upward, the stars seem to sit together on a dark surface. Constellations reinforce that impression. Stars that appear almost side by side can actually lie at very different distances from Earth. The sky is effectively a two-dimensional projection of a deeply three-dimensional distribution. One star may be 10 light years away, another that appears beside it may be 50, another may be hundreds or thousands. Their apparent positions overlap only because we are looking from one particular viewpoint. If we could move dozens of light years sideways through the galaxy and look back, the familiar constellations would distort and eventually disappear. Now expand the imaginary sphere around the Sun from 10 light years to 20. The radius has doubled, but the amount of space inside has increased much more dramatically. The volume of a sphere grows with the cube of its radius, so doubling the radius does not merely double the volume, it increases it by a factor of 8. Stretch the radius to 50 light years and the surrounding volume becomes vastly larger again. Extend it to 100 light years and our local stellar neighborhood contains thousands upon thousands of stars. The numbers become easier to appreciate when light itself is used as the clock. A star 10 light years away is seen as it was 10 years ago. If something changed there tonight, we would not know about it for another 10 years. A star 50 light years away appears as it was half a century ago. A star 100 light years away is being shown to us by light that began its journey around a century before it reaches our eyes. Distance is now also look-back time. The farther we see, the farther into the past we see. This effect was present even with the Moon and the Sun, but there the delay was tiny. The Moon appeared roughly 1.3 seconds in the past. The Sun appeared a little more than 8 minutes in the past. Proxima Centauri appears more than 4 years in the past. At 100 light years, the delay is longer than a typical human lifetime. Imagine looking at a star 100 light years away tonight. The light entering your eyes may have left that system before many people alive today were born. If someone there could somehow see Earth at the same distance with a sufficiently powerful telescope, they would not see our present. They would receive light from Earth that left a century earlier. The two locations could exist at the same cosmic moment while observing very different versions of one another. This is not because time itself is delayed between them. It is because information cannot cross the distance faster than light. The local stellar neighbourhood is therefore not something we can ever observe completely as it is now. Every direction carries information from a slightly different moment in the past. To work out where these stars actually are in three-dimensional space, astronomers need precise distance measurements. Stellar parallax remains one of the most direct methods for nearby stars. As Earth travels around the Sun, our viewing position changes. Nearby stars appear to shift slightly against more distant background stars. The smaller the apparent shift, the farther away the star generally is. The European Space Agency Gaia mission transformed this kind of measurement. Gaia repeatedly measured the positions, motions and brightnesses of enormous numbers of stars with extraordinary precision. Its observations allowed astronomers to construct a far more detailed three-dimensional map of the Milky Way than was possible before. Instead of treating the night sky as a flat collection of points, these measurements place stars at different depths. Suddenly the sky gains structure. Some neighbours lie only a handful of light years away. Others occupy shells tens or hundreds of light years from the Sun. And the farther those shells extend, the more stars and more empty space they contain. 100 light years sounds enormous because it is. Light itself requires a century to cross it. Voyager 1, travelling at its current kind of speed, would require well over 1,000,000 years to cover such a distance. Yet 100 light years is still considered local when discussing the Milky Way. That is the scale shift now taking place. Proxima Centauri, once separated from us by a staggering 40 trillion kilometres, has become almost the first house down the road. A sphere 100 light-years across is vastly larger than anything in the solar system. Yet even that region occupies only a tiny portion of our galaxy. The Milky Way stretches not for hundreds of light-years, but for tens of thousands. Soon, individual nearby stars will no longer be large enough to act as useful landmarks. The next ruler will not be a planetary orbit, or even the distance between neighbouring suns. It will be the galaxy itself. Once the scale reaches hundreds of light years, individual stars begin to lose their usefulness as landmarks. The distances are still enormous, but the larger structure around them is becoming more important. That structure is the Milky Way. The Milky Way is a barred spiral galaxy containing hundreds of billions of stars, along with gas, dust, stellar remnants, planets, dark matter, and the enormous empty spaces between them. Its visible stellar disk is roughly 100,000 light-years across. That number is not a perfectly sharp boundary. Galaxies do not end like buildings or countries. Their stars gradually become more sparse with distance, while gas and dark matter extend beyond the brightest parts of the disk. So when astronomers describe the Milky Way as being roughly 100,000 light-years across, they are usually talking about the broad scale of its main stellar structure, rather than a precise outer wall. Even so, 100,000 light-years is enough to transform everything we have encountered so far. The solar system lies roughly 26,000 light-years from the galactic centre. That means the centre of our own galaxy is more than 6,000 times farther away than Proxima Centauri. And Proxima Centauri had already seemed almost impossibly distant. Light requires a little over 8 minutes to travel from the Sun to Earth. It takes more than 4 years to travel from Proxima Centauri. It takes around 26,000 years to travel between our region of the galaxy and the galactic centre. The same thing as travelling in every case. Only the distance changes. Imagine sending a message toward the centre of the Milky Way using the fastest possible carrier of information. Even if the message travelled at the speed of light, it would need roughly 26,000 years to arrive. Suppose someone there received it and replied immediately. Their response would require another 26,000 years to return. the conversation would take roughly 52,000 years. A simple question followed by a perfectly prompt answer could span longer than the entire history of human civilization. That gives some sense of what galactic distance actually means. Our 100 light-year neighborhood, which already contained thousands of stars and stretched beyond a human lifetime even for light, is now a tiny patch within something roughly 1,000 times wider. At this scale, astronomers often use another unit called the parsec. The parsec is closely connected with stellar parallax. 1 parsec is the distance at which an astronomical unit would subtend an angle of 1 arcsecond. In more familiar terms, 1 parsec is roughly 3.26 light-years. Astronomers commonly use parsecs, kiloparsecs and eventually megaparsecs, because these units connect naturally with the way many stellar and galactic distances are measured. For a general sense of scale, however, light-years have one special advantage. They immediately tell us how long light takes to cross a distance. A star 1,000 light-years away is seen by light that has travelled for 1,000 years. The galactic centre is seen through light and other electromagnetic radiation that began travelling toward us around 26,000 years ago. And if we could somehow see directly across the full diameter of the Milky Way, the information from the far side could be tens of thousands of years older still. This creates an unusual difficulty. We live inside the galaxy we are trying to map. From outside, a spiral galaxy can be photographed as a complete object. We cannot simply move a camera a few 100,000 light-years away and take a picture of the Milky Way from above. Every map of our galaxy has to be reconstructed from measurements made within it. The European Space Agency Gaia mission has played an enormous role in this effort. By measuring the positions, motions and distances of vast numbers of stars, Gaia has helped reveal the structure of the stellar disk and the movement of stars through the galaxy. But visible starlight is only part of the story. Dust can block our view across large regions of the Milky Way. Infrared astronomy allows astronomers to see through much of that dust, because infrared radiation passes through dusty regions more easily than visible light. Radio astronomy provides another view. Neutral hydrogen gas produces a characteristic radio signal that allows astronomers to trace gas throughout the galactic disk. By measuring its motion and distribution, researchers can infer large-scale structures that would otherwise be difficult to see from our position inside the galaxy. Toward the centre lies a particularly important radio source known as Sagittarius A star. Sagittarius A star is associated with the supermassive black hole at the heart of the Milky Way. That central black hole has a mass of roughly 4 million suns, but for distance, the remarkable fact is simpler. When astronomers observe Sagittarius A star, they are seeing information that has travelled for around 26,000 years. The centre we observe is not the galactic centre as it exists at this exact moment. It is the galactic centre as it was roughly 26,000 years ago. This is becoming unavoidable now. Distance and history are merging. Every extra light year outward is also another year backward in the information we receive. The Milky Way becomes even more difficult to imagine if we shrink it. Suppose the entire galaxy were reduced until its 100,000 light-year width fitted across a large city. The solar system would not become a little marble. It would not become a grain of sand. On that scale, the region containing the planets would be effectively microscopic. Even the enormous possible Oort cloud would disappear into something far too small to notice. The distance to Proxima Centauri would also become tiny compared with the galactic disk. Our entire local stellar neighbourhood would occupy only a small patch. This is the same pattern that has repeated again and again. Earth seemed enormous until the Moon provided a larger reference. The Earth-Moon distance seemed enormous until the Sun reduced it. The solar system seemed enormous until interstellar space reduced that. And now a 100-light-year neighborhood containing thousands of stars has become almost negligible within one galaxy. Yet the Milky Way itself is not remotely the largest useful reference. Its roughly 100,000 light-year width is about to become another ordinary measuring stick, because beyond the Milky Way lie other galaxies. Some are close enough to be gravitational companions, others are separated from us by millions of light-years, and once those distances enter the picture, even a beam of light taking 100,000 years to cross our entire galaxy will begin to seem surprisingly local. The Milky Way feels enormous until we begin to step beyond it. Our galaxy stretches roughly 100,000 light-years across its main stellar disk, and the solar system sits around 26,000 light-years from the galactic center. But even the Milky Way is not isolated. Around it are smaller companion galaxies, some gravitationally bound to our own, and moving through the larger galactic environment like satellites around a much greater structure. Two of the most famous are the Large Magellanic Cloud and the Small Magellanic Cloud. The Large Magellanic Cloud lies roughly 160,000 light-years from Earth. The Small Magellanic Cloud is farther away, at roughly 200,000 light-years. Those distances are already large enough that the Milky Way itself can begin to serve as a measuring stick. If the main stellar disk of the Milky Way is around 100,000 light-years across, then the Large Magellanic Cloud is roughly 1.5 Milky Way widths away from us. The Small Magellanic Cloud is roughly 2 Milky Way widths away. That comparison matters, because a whole galaxy has now become something small enough to use as a unit. Not long ago, crossing the Milky Way sounded almost absurd. Light itself would need around 100,000 years to travel from one side of the main disk to the other. Now we are discussing distances where multiple Milky Way diameters fit between one galaxy and another, and, as before, distance is also telling us how far into the past we are looking. The light reaching us from the Large Magellanic Cloud has been travelling for roughly 160,000 years. The light from the Small Magellanic Cloud has travelled for about 200,000 years. That means when astronomers observe these galaxies tonight, they are not seeing them as they are now. They are seeing versions of them from long before modern civilization existed. In fact, the information crossing those distances began its journey before Homo sapiens had spread across much of the world. This is one of the strange consequences of large astronomical distance. The farther away we look, the less recent the picture becomes. The universe is not showing us one single present moment. It is showing us layers of the past, with the age of the light increasing as the distance grows. The Milky Way itself also extends beyond the bright spiral disk that is easiest to imagine. Surrounding the visible galaxy is a much larger galactic halo. This halo contains old stars, globular clusters, streams of stars pulled from smaller systems, and many dwarf galaxies associated with the Milky Way. The dark matter halo is thought to extend farther still, so even saying where the Milky Way ends is not perfectly simple. The bright disk has one scale, the stellar halo has another. The dark matter halo extends over a much larger region. Some globular clusters and satellite galaxies orbit at enormous distances from the galactic center, while still remaining gravitationally connected to the Milky Way. This means a galaxy is not really a neat glowing island with a clean outer edge. Photographs can make it look that way, because most of the visible light is concentrated in the bright central regions and disk, but gravitationally, the structure spreads much farther into surrounding space. The Large Magellanic Cloud provides a particularly useful example of how distance and time combine. In 1987, astronomers observed a supernova in the Large Magellanic Cloud. It became known as supernova 1987A. The explosion appeared in Earth's sky in 1987, but that was not when the star actually exploded. The Large Magellanic Cloud is roughly 168,000 light-years away in the direction of the supernova, so the star had actually exploded around 168,000 years earlier. The light from that event had been travelling through space for all that time before finally reaching Earth. For nearly 170,000 years, the evidence of the explosion was already on its way toward us. Then, in 1987, it arrived. This makes the idea of look-back time much more concrete. A distant event can be long over before anyone on Earth knows it happened. The delay is not caused by poor instruments. It is built into the distance itself. Information takes time to travel. And at these scales, that time can be longer than the entire history of civilization. The same principle applies to every star and galaxy we observe. A galaxy 1 million light-years away is seen 1 million years in the past. A galaxy 10 million light-years away is seen 10 million years in the past. Eventually, when distances reach billions of light-years, the light we receive will show the universe when it was genuinely young. But before reaching those scales, there is another important step. The Magellanic Clouds are still close enough to be associated with the Milky Way. They belong to our immediate galactic neighbourhood. Beyond them, the distances begin to expand much more dramatically. The Andromeda galaxy lies roughly 2.5 million light-years away. That is not merely a little farther than the Magellanic Clouds, it is more than 10 times farther. The difference between 160,000 light-years and 2.5 million light-years is the same kind of scale change we have encountered repeatedly. The larger distance does not simply add more space. It changes what counts as nearby. A whole Milky Way once seemed impossibly large. Now several Milky Way diameters can fit into the distances around our immediate galactic environment, and soon even millions of light-years will begin to sound local. Andromeda marks the point where hundreds of thousands of light-years give way to millions. The Andromeda galaxy lies roughly 2.5 million light-years from Earth. That is around 25 times the diameter of the Milky Way's main stellar disk. A whole galaxy that once seemed almost impossibly large can now be placed end to end again and again across the space separating us from another major galaxy. Imagine the Milky Way as a disk about 1 meter wide. On that scale, Andromeda would not be sitting just beside it. It would be roughly 25 meters away. Most of the space between the two would contain almost nothing visible at all. The comparison immediately reveals something that photographs tend to hide. Galaxies are not crowded together like lights in a city. Even within a region where galaxies are gravitationally associated, the gaps between them are immense. Andromeda is close enough to be visible to the unaided eye under dark skies. It appears as a faint smudge. That makes its true distance especially strange. The light entering your eyes from Andromeda tonight began travelling roughly 2.5 million years ago. At that time, Earth was a very different place. Early members of the human genus were already living in Africa. But modern civilization was still unimaginably far in the future. No cities existed. No written language existed. No one had ever looked toward Andromeda and wondered how far away it was. Yet the photons we see tonight were already moving through intergalactic space. For roughly 2.5 million years they travelled. Then, finally, some of them reached Earth. So when we look at Andromeda, we are not looking across space alone. We are looking across a substantial portion of human evolutionary history. And even Andromeda is not isolated. The Milky Way and Andromeda belong to a larger gravitationally associated collection known as the Local Group. The Local Group contains the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. Its overall extent is on the order of 10 million light-years. That means the distance to Andromeda, enormous as it is, represents only part of the wider region occupied by our local collection of galaxies. 10 million light-years is a difficult number to visualize. Light could cross the entire Milky Way in roughly 100,000 years. To cross 10 million light-years, it would need around 100 times longer. A beam of light could traverse a galaxy like the Milky Way over and over before crossing a distance comparable to the scale of the Local Group. And yet the Local Group itself contains enormous amounts of emptiness. The galaxies occupy only tiny fractions of the total volume. Most of the region is intergalactic space. This is the same pattern seen earlier, but magnified enormously. The Earth and Moon were separated by mostly empty space. The planets were separated by much larger empty regions. Stars were separated by light-years of emptiness. Now entire galaxies are separated by millions of light-years. The objects grow larger, but the gaps grow faster. At these distances, another problem appears. How do astronomers actually know how far away Andromeda is? Stellar parallax works beautifully for nearby stars, but the farther a star lies from Earth, the smaller its apparent parallax becomes. Eventually, the angular shift is so tiny that another method is needed. One of the most important breakthroughs came from Henrietta Swan Leavitt. While studying variable stars in the Small Magellanic Cloud in the early 20th century, Leavitt noticed a remarkable relationship among a class of pulsating stars known as Cepheid variables. Cepheid variables brighten and dim in a regular cycle. Leavitt found that the length of this cycle is related to the star's intrinsic luminosity. Cepheids with longer periods are intrinsically more luminous than those with shorter periods. This became known as the period-luminosity relationship. Its importance was enormous. If astronomers measure how quickly a Cepheid pulsates, they can infer how luminous it really is. They can then compare that intrinsic brightness with how faint the star appears from Earth. The greater the difference, the farther away the star must be. This provided astronomy with a powerful new distance indicator. Cepheid variables could reach much farther than ordinary stellar parallax. And Andromeda became one of the most important places where this technique changed our understanding of the universe. In the early 20th century, astronomers were still debating the nature of objects then called spiral nebulae. Some argued that these spirals were structures inside the Milky Way. Others suspected that they were separate systems of stars far beyond our galaxy. Edwin Hubble identified Cepheid variable stars in Andromeda during the 1920s. Their brightness and pulsation periods showed that Andromeda was far too distant to lie inside the Milky Way. It was another galaxy. The universe had suddenly become much larger. The Milky Way was no longer the entire stellar universe. It was one galaxy among many. This also illustrates the beginning of what astronomers call the cosmic distance ladder. There is no single measuring tape that stretches from Earth to the farthest observable galaxies. Instead, different methods work across different ranges. Nearby distances can be measured geometrically. Stellar parallax reaches nearby stars. Cepheid variables extend the scale farther outward. Other techniques eventually take over across still greater distances. Each method overlaps with another, allowing the scale to be calibrated step by step. In that sense, cosmic distance is not measured by one enormous leap. It is built like a ladder. Each rung depends partly on the reliability of the ones below it. Andromeda sits at an important point on that ladder. At roughly 2.5 million light-years, it is close enough for individual stars to be studied, yet far enough to demonstrate unmistakably that the Milky Way is only one member of a much larger universe. For the moment, millions of light-years feel enormous. The local group stretches across roughly 10 million. Andromeda itself lies 2.5 million away. Light takes millions of years to move between neighbouring major galaxies, but even this scale will not remain impressive for very long. Beyond the local group lie galaxy clusters containing hundreds or thousands of galaxies. Their distances are measured not in a few million light-years, but in tens of millions. And once those structures enter view, even Andromeda begins to feel remarkably close. The local group feels enormous until we compare it with a true galaxy cluster. The Virgo cluster lies roughly 50 to 60 million light-years from Earth. That distance is so much larger than the 2.5 million light-years to Andromeda that our nearest large galactic neighbour suddenly begins to feel almost local. You could place the Earth to Andromeda distance, end to end, more than 20 times before reaching the central region of the Virgo cluster. And remember what that earlier distance already meant. Light from Andromeda takes roughly 2.5 million years to reach us. Light from Virgo can require more than 50 million years. The same light that crosses Earth in a fraction of a second now spends tens of millions of years travelling through intergalactic space. By the time that light arrives, the world it left behind may have changed enormously. The light we receive from galaxies in Virgo today began travelling long before human beings existed. Go back 50 million years on Earth and there were no humans, no apes, and no human ancestors in anything like their later form. Mammals were diversifying after the extinction of the non-avian dinosaurs, and the planet was moving through a very different chapter of biological history. Yet while all of that unfolded on Earth, photons from the Virgo cluster were already crossing the darkness toward us. The Virgo cluster itself contains many galaxies bound together by gravity. Some are enormous elliptical galaxies, others are spirals. Many are much smaller dwarf galaxies. But the visible galaxies are only part of the cluster. They move within a much larger gravitational environment containing enormous amounts of dark matter, along with extremely hot gas spread through the space between galaxies. This hot intracluster gas can emit strongly in X-rays and contains a tremendous amount of ordinary matter, even though it is almost invisible to human eyes. A galaxy cluster is therefore not simply a pile of galaxies. It is a gravitational structure spanning millions of light-years, and once an entire cluster enters the picture, the Milky Way becomes a very small reference object. The main stellar disk of the Milky Way is roughly 100,000 light-years across. The Virgo cluster is tens of millions of light-years away. So the distance to Virgo corresponds to hundreds of Milky Way diameters. The galaxy that once seemed unimaginably large has now become something that could be repeated across the gap hundreds of times. The Earth-Sun distance has become even less useful. One astronomical unit is roughly 150 million kilometers. That number once seemed vast enough to require a new unit. Now a single astronomical unit is so tiny compared with intergalactic distance that using it here would be like measuring the width of a continent in grains of sand. The mathematics would work. The comparison would not help. This is why the scale of astronomy keeps replacing its own rulers. Meters gave way to kilometers. Kilometers gave way to astronomical units. Astronomical units gave way to light years. and now even single light years are becoming too small to carry the scale comfortably. At tens of millions of light years, measuring distance also becomes more difficult. Stellar parallax is extraordinarily useful nearby, but eventually the apparent positional shifts of stars become far too small to measure effectively. Cepheid variable stars extend the distance ladder farther. Henrietta Swan Leavitt's discovery of the relationship between a Cepheid variable star's pulsation period and its intrinsic luminosity gave astronomers a powerful way to estimate distances well beyond the range of ordinary parallax. Edwin Hubble later used Cepheid variables in Andromeda to show that it lay far beyond the Milky Way. Walter Baade helped improve the calibration of the extragalactic distance scale by recognizing that different stellar populations had been confused in earlier work, leading to important revisions in estimates of galactic distances. But even Cepheids have limits. At still greater distances, astronomers need brighter markers. One of the most important is the Type 1a supernova. These explosions occur in systems involving white dwarf stars and can become extraordinarily luminous, sometimes shining as brightly as an entire galaxy for a short time. Their usefulness comes from the fact that their peak luminosities can be standardized. Astronomers observe how bright a Type 1a supernova appears, account for known relationships in its light curve, and compare the observed brightness with the calibrated intrinsic brightness. The fainter it appears, after relevant corrections, the farther away it generally is. This allows Type 1a supernovae to extend the cosmic distance ladder far beyond the range of ordinary Cepheid measurements. The method became especially important in the late 20th century, when observations of distant supernovae helped reveal that the expansion of the universe is accelerating, but even before reaching those enormous scales. The Virgo cluster already changes our sense of distance. A cluster is not the final large structure in the universe. Clusters themselves are separated by huge intergalactic regions. Some gather into broader associations. Between them lie cosmic voids where the density of galaxies is far lower. The universe begins to look less like isolated objects scattered evenly through space, and more like a vast network of dense regions separated by immense emptiness. That emptiness can be tens of millions of light-years across. At this scale, a distance of 1 million light-years no longer sounds especially dramatic. It begins to resemble a local measurement. Andromeda lies roughly 2.5 million light-years away. The local group extends across around 10 million light-years. Virgo lies more than 50 million light-years from us. The progression is still accelerating. Earth itself is now effectively meaningless as a scale reference. The solar system has vanished into the distance. The nearest stars have vanished. Even the Milky Way has become a small object inside a much larger map. And the Virgo cluster, enormous as it seems, is not an isolated island. Once we widen the view again, individual clusters begin to appear as parts of structures spanning hundreds of millions of light-years. At that point, even tens of millions of light-years begin to feel surprisingly small. Once galaxy clusters become familiar, the universe begins to reveal a much larger pattern. Galaxies are not scattered randomly through space like isolated lights thrown across a dark background. Instead, they gather into groups and clusters, and those clusters themselves tend to lie along enormous filaments. Between those filaments are vast regions containing far fewer galaxies. Taken together, this structure is known as the cosmic web. At smaller scales, gravity pulls matter together into stars, galaxies and clusters. Across billions of years, the same gravitational process has shaped matter on much larger scales as well. regions that began slightly denser than average attracted more matter. Those dense regions grew, galaxies formed within them, clusters developed where concentrations became particularly large, and eventually a web-like pattern emerged across the observable universe. The scale is difficult to appreciate because even a galaxy cluster, which already spans millions of light-years, becomes only a knot within this wider network. Filaments of galaxies can stretch for tens or hundreds of millions of light-years. Dense clusters tend to appear where several filaments meet. Between them lie enormous cosmic voids. A useful reference point is 100 million light-years. The main stellar disk of the Milky Way is roughly 100,000 light-years across, so a distance of 100 million light-years is about 1,000 Milky Way diameters. Imagine placing 1,000 galaxies the width of our own side by side. That would finally produce a line around 100 million light-years long. And even that distance is no longer exceptional when discussing the cosmic web. Our own wider cosmic environment provides an example. The Milky Way belongs to the local group. The local group lies within a much larger region of galaxy motions that astronomers have called the Laniakea supercluster. Laniakea spans roughly 500 million light-years, that is around 5,000 Milky Way diameters. The name refers not to one single tightly bound object, but to a vast region identified by studying how galaxies move through space. This distinction is important. A galaxy is gravitationally bound. A galaxy cluster is gravitationally bound. But a supercluster does not necessarily behave like one enormous object that will eventually collapse into itself. Cosmic expansion and local gravitational attraction compete across these immense distances. The boundaries of a supercluster are therefore much less definite than the edge of a planet, a star, or even a galaxy. Laniakea was identified by examining the peculiar velocities of galaxies, meaning the motions they have in addition to the general expansion of the universe. Those motions reveal how matter is flowing through the surrounding cosmic landscape. Within this region lies an area commonly called the Great Attractor. The Great Attractor is not one mysterious object dragging everything toward it. It is a region of enhanced gravitational influence associated with a much larger concentration of mass. The Milky Way and many neighbouring galaxies have motions affected by this wider distribution. The Great Attractor lies roughly a couple of 100 million light-years away, although the structure involved is broad rather than a single point with one perfectly defined distance. Again, millions of light-years have become the language of the local neighbourhood. The emptier regions are just as impressive. Cosmic voids can span tens of millions of light-years, and some are larger still. Imagine a region many hundreds of times wider than the Milky Way, containing comparatively few luminous galaxies. The word void can make such places sound completely empty, but they are not. They contain some matter, some galaxies, gas, dark matter, and radiation. They are simply far less dense than the filaments and clusters around them. This creates one of the strangest changes in perspective so far. Earlier, the emptiness between Earth and the Moon seemed enormous. Then the space between planets made that gap look small. Interstellar space reduced the entire solar system to a compact region. Intergalactic space reduced individual stars to irrelevance. Now there are comparatively empty regions large enough to contain thousands of Milky Way-sized galaxies across their width. The scale has become almost detached from anything human experience can provide. Astronomers discovered this large-scale organization by mapping enormous numbers of galaxies. One of the most important projects has been the Sloan Digital Sky Survey. By measuring the positions and spectra of millions of astronomical objects, Surveys like this have allowed astronomers to construct three-dimensional maps extending across enormous regions of the universe. Those maps reveal filaments, walls, clusters and voids, rather than a smooth random distribution. Distance measurements at these scales also begin to rely increasingly on redshift. When light from a distant galaxy reaches us, its wavelength is often stretched toward the red end of the spectrum. For very distant galaxies, much of this redshift results from the expansion of space while the light travels toward us. In general, greater cosmological redshift corresponds to greater distance and greater look-back time. But the relationship is no longer as simple as saying that light travelled for a certain number of years, therefore the galaxy must now be that many light years away. The universe has been expanding during the journey. The distance between us and the galaxy can change while the light is travelling. At relatively nearby cosmological scales, astronomers can relate recession and distance using the expansion of the universe. Farther away, the full expansion history becomes increasingly important. So even the meaning of distance itself is beginning to become more complicated. An individual galaxy has also almost disappeared from the mental picture. At the scale of hundreds of millions of light years, a galaxy like the Milky Way becomes little more than a point within a filament. The local group becomes a tiny concentration. Even the Virgo cluster becomes one feature among many. This is the same transformation that happened to Earth, then the solar system, then nearby stars, and then the Milky Way. Each object remains physically enormous. It only seems small because the reference frame around it has expanded. 500 million light-years feels almost impossibly large. Light would need 500 million years to travel such a distance through static space. Human civilization occupies only the faintest fraction of that duration. Yet even hundreds of millions of light-years do not take us to the largest useful scales. The next step is not another 10 million. It is not another 100 million. It is the point where 1 billion light-years becomes a natural distance to discuss. And once that happens, the cosmic web itself begins to look local. 1 billion light-years is the point where distance begins to stop behaving like a simple gap between two places. Up to this scale, it has been possible to imagine space rather neatly. Earth is here. The moon is farther away. The sun is farther still. Then come the planets, the nearest stars, the Milky Way, neighbouring galaxies, clusters, and the great filaments of the cosmic web. Each time, the number grows. But once the scale reaches 1 billion light-years, the universe itself begins to change while the light is travelling through it. First, though, it is worth pausing on the number. 1 billion light-years is the distance light would travel through empty, non-expanding space during 1 billion years. 1 billion years. The Milky Way is roughly 100,000 light-years across, so 1 billion light-years corresponds to about 10,000 Milky Way diameters. Andromeda lies roughly 2.5 million light-years from Earth. You could repeat that distance around 400 times before reaching 1 billion light-years. The local group, spread across roughly 10 million light-years, would fit into the same distance around 100 times. The cosmic structures that recently seemed almost impossible to imagine are beginning to occupy surprisingly small fractions of this new ruler. Even time starts to lose its ordinary meaning. If light has travelled for around 1 billion years before reaching us, then it began its journey at a time when Earth looked nothing like the world outside your window tonight. 1 billion years ago, there were no humans, there were no mammals, there were no dinosaurs. Complex animal life had not yet appeared in the familiar forms that would eventually fill Earth's oceans and continents. Most life was microscopic, A beam of light beginning its journey then could travel continuously through space, while almost the entire visible history of complex life on Earth unfolded. It could keep travelling while animals diversified, while life moved on to land, while forests appeared, while dinosaurs rose and disappeared, while mammals expanded into new ecological roles, and while eventually humans appeared. Only then would that ancient light finally arrive, and yet 1 billion light-years does not carry us into an empty universe. Quite the opposite. Large astronomical surveys reveal galaxies across enormous volumes of space. Millions of galaxies can be mapped when observations cover wide enough regions and extend deeply enough into the cosmos. At these scales, individual galaxies become tiny points in three-dimensional maps. Their positions reveal the larger cosmic web of filaments, clusters and voids. The universe continues to contain structure. The difficulty is that understanding the distances to those structures becomes more subtle. One of the major clues comes from the relationship between distance and cosmic expansion. In the 1920s, astronomers were building upon observations showing that light from many distant galaxies was shifted toward longer, redder wavelengths. Georges Lemaitre developed an expanding universe model based on Albert Einstein's general theory of relativity and connected this expansion with the observed recession of galaxies. Edwin Hubble later published observational evidence showing a relationship between the distances to galaxies and their recession velocities. Today this relationship is commonly called the Hubble-Lemaitre law. In broad terms, galaxies that are farther away tend to recede from us more rapidly as part of the overall expansion of the universe. But this does not mean Earth is sitting at the centre of an enormous explosion with galaxies flying away through otherwise static space. That image is tempting, but misleading. On the largest scales, space itself is expanding. The average distance between widely separated, gravitationally unbound regions increases with time. From another distant galaxy, an observer would see the same broad pattern of other distant galaxies receding. There is no known central point in ordinary three-dimensional space from which everything was launched. A common comparison is a loaf of raisin bread expanding as it bakes. As the dough expands, every raisin becomes farther from the other raisins. No individual raisin has to be the central one. The universe is more complicated than bread, fortunately, but the comparison captures the idea that separation can increase because the space between objects changes. And that creates a problem for distance. Suppose light leaves a distant galaxy and begins travelling toward Earth. During its journey, the universe continues expanding. The galaxy that emitted the light can therefore be farther away today than it was when the light began travelling. This means several different numbers can describe the same remote object. There is look-back time, which tells us how long the light has been travelling. There is the distance the light effectively covered along its changing path. There is the distance to the galaxy when the light was emitted. There is the galaxy's present-day distance within the expanding universe. And there is comoving distance, a cosmological way of describing separation while accounting for expansion. These numbers do not always agree. At nearby scales, the differences are small enough that ordinary language works reasonably well. If a star is 10 light-years away, saying that its light has travelled for about 10 years gives an intuitive picture. But at distances approaching billions of light-years, the expansion history of the universe matters. A galaxy whose light has travelled for 1 billion years is not necessarily exactly 1 billion light-years away today. Its current separation can be larger because additional space developed between us while the photons were in transit. Redshift helps astronomers study this expansion. As space expands, the wavelength of light travelling through it is stretched. The farther that expansion proceeds during the journey, the more pronounced the cosmological redshift can become. Astronomers can measure the spectrum of a distant galaxy, identify familiar features within it, and determine how much those features have shifted toward longer wavelengths. That redshift can then be interpreted using cosmological models to estimate the galaxy's place in the expanding universe. So distance has changed character. Earlier, the difficulty was simply the size of the number. 40 trillion kilometers to Proxima Centauri sounded unreasonable, so the light year became more convenient. Millions of light years then became ordinary when galaxies entered the picture. Hundreds of millions followed as the cosmic web emerged. Now at around 1 billion light years, the challenge is no longer merely finding a bigger ruler. We have to specify what kind of distance we mean. And even 1 billion light years is not especially close to the maximum scale available to us. The observable universe extends vastly farther. Light has been travelling toward us for more than 10 billion years from some of the most distant regions we can observe. So 1 billion light years, extraordinary as it sounds, is not the end of the scale. It is the point where the final truly cosmological distances begin. 1 billion light years is difficult to imagine. 10 billion light years is something else entirely. At this scale, the distance is so great that the light reaching us has spent most of the history of the universe in transit. The universe is approximately 13.8 billion years old. So when astronomers observe an object whose light has travelled for 10 billion years, they are not simply looking at something very far away. They are looking at the universe when it was much younger. The distinction matters because distance and time have now become inseparable. A galaxy whose light has travelled for 10 billion years is seen as it existed 10 billion years ago. We are not seeing what that galaxy looks like today. We are seeing ancient information that has only just arrived. And 10 billion years is already more than twice the age of the solar system. The Sun and planets formed roughly 4.6 billion years ago. That means some of the light reaching our telescopes tonight had already been travelling through space for more than 5 billion years before the Sun even existed. Before Earth formed, the photons were already on their way. Before the first ocean appeared on our planet, they were travelling. Before life began here, they had already crossed enormous regions of the cosmos, and they still had billions of years left to go. This is one reason extremely distant galaxies are so valuable to astronomers. Looking farther away allows us to study earlier periods of cosmic history. The Hubble Space Telescope transformed this kind of observation. By staring for long periods at seemingly unremarkable regions of the sky, it revealed thousands of faint galaxies at enormous distances. Some appeared as they were many billions of years ago. The James Webb Space Telescope has extended that view even farther into the early universe. Its large mirror and sensitivity to infrared light allow it to detect galaxies whose radiation has been stretched enormously during its journey through expanding space. Some of these galaxies are seen as they existed only a few 100 million years after the Big Bang. Their light has travelled for more than 13 billion years. But this is where the language becomes slightly awkward. It is tempting to say that such a galaxy is simply 13 billion light-years away. That sounds reasonable. If its light travelled for 13 billion years, surely the distance must be 13 billion light-years. In an unchanging universe, that would be a useful approximation. But the universe is not unchanging. Space has expanded while the light travelled. The galaxy that emitted those photons continued participating in the large-scale expansion of the universe as the photons made their way toward us. As a result, the present-day distance to that galaxy can be much larger than the number of years its light has travelled. This is why cosmologists distinguish between different meanings of distance. Look-back time describes how long the light has been travelling. Light travel distance gives an intuitive sense of the journey the photons have made. Comoving distance describes the present-day separation between distant locations while taking cosmic expansion into account. And the distance between us and the galaxy when the light was originally emitted was different again. At modest distances, these distinctions may not greatly affect ordinary conversation. At 10 billion light-years and beyond, they become essential. Redshift helps astronomers place these distant galaxies within cosmic history. Light has a wavelength. As space expands during the journey of a photon, that wavelength can be stretched along with the expanding universe. The result is cosmological redshift. Light that was originally emitted at shorter wavelengths can arrive at Earth shifted toward much longer wavelengths. For very distant galaxies, radiation originally emitted in visible or ultraviolet light may arrive primarily in the infrared. This is one reason the James Webb Space Telescope is so effective at studying the early universe. It was designed to observe strongly in infrared wavelengths. The amount of cosmological redshift can be measured by examining a galaxy's spectrum. Atoms and molecules produce recognizable spectral features at known wavelengths. When astronomers find those same features shifted toward longer wavelengths, they can determine how much the light has been stretched. Large redshifts generally correspond to objects seen much earlier in cosmic history. But redshift does not translate into one simple distance without a model of how the universe has expanded. That model depends upon the contents and history of the cosmos. Modern cosmology describes a universe containing ordinary matter, dark matter, and dark energy. Together with radiation and other contributions that were more important during earlier eras, their relative influence affects how the expansion rate changes with time. The theoretical foundations of an expanding universe developed from Albert Einstein's general theory of relativity. Alexander Friedmann found solutions to Einstein's equations describing universes that could expand or contract. Georges Lemaitre independently developed expanding cosmological models and connected them with astronomical observations. These ideas eventually became part of the foundation of modern cosmology. The important point for distance is that the expansion has not proceeded at one perfectly constant rate throughout cosmic history. The early universe evolved differently from the later universe. Matter dominated the dynamics for a long period. At more recent cosmic times, dark energy has become increasingly important in the large-scale expansion. So when astronomers measure the redshift of a galaxy, estimating its distance requires knowledge of that expansion history. This makes extremely distant objects fundamentally different from nearby stars. Proxima Centauri lies a little over 4 light-years away. Its distance can be understood quite comfortably as a spatial gap. At cosmological distances, space itself has changed significantly during the journey. Some of the most spectacular markers at these distances are quasars. Quasars are intensely luminous regions surrounding actively feeding supermassive black holes in distant galaxies. Matter falling toward the central black hole becomes extremely hot and can release tremendous amounts of radiation. This extraordinary brightness allows quasars to be seen across billions of light-years. Many known quasars are observed at look-back times exceeding 10 billion years. When their light arrives, it brings information from an era when galaxies and their central black holes were developing very differently from those nearby today. Deep observations also reveal increasingly young galaxies. Some appear smaller, more irregular, and more actively star-forming than many mature galaxies in the nearby universe. Their appearance is not simply the result of distance. We are genuinely seeing them at an earlier stage of cosmic evolution. This is perhaps the most remarkable property of very large distances. A powerful telescope is also, in a very real sense, a machine for looking backward in time. Not because it travels into the past, but because the information arriving from distant objects is old. At 1 million light years, the look back is 1 million years. At 1 billion light years, it becomes a billion. At 10 billion, most of cosmic history lies between the event we observe and the moment we observe it. And eventually, even galaxies and quasars begin to run out. There is a time in the early universe before ordinary galaxies existed. There is an even earlier period when the universe was so hot and dense that light could not travel freely at all. That creates a much more fundamental observational boundary. Beyond the most distant galaxies lies radiation that has been travelling almost since the universe first became transparent. It does not come from a star. It does not come from a galaxy. It fills the sky in every direction, and it represents the oldest electromagnetic light we can directly observe. There is a point beyond which ordinary light from stars and galaxies can no longer take us. No matter how powerful the telescope becomes, there is an earlier period of the universe that cannot be revealed simply by finding a more distant galaxy. Instead, the oldest electromagnetic radiation we can directly observe comes from a time when the universe itself first became transparent. This radiation is known as the cosmic microwave background. It reaches Earth from every direction in the sky, carrying information from roughly 380,000 years after the Big Bang. That sounds extremely early, and it is. The universe today is around 13.8 billion years old, so 380,000 years represents only a tiny fraction of its history. But before that moment, conditions were very different. The early universe was much hotter and denser than it is today. Matter existed largely as an ionized plasma containing free electrons and atomic nuclei. Photons were present everywhere, but they could not travel freely for long distances. Free electrons repeatedly scattered the light. A photon might move briefly through the plasma, encounter an electron, scatter in another direction, and continue this process again and again. The universe was therefore opaque. It was filled with light, but that light could not simply cross space uninterrupted and arrive at a distant observer. As the universe expanded, it cooled. Eventually the temperature fell enough for electrons to combine with atomic nuclei, particularly protons, forming neutral hydrogen atoms. This stage is known as recombination. The name is slightly historical, because the electrons and nuclei were not necessarily combining for a second time, but the term remains standard in cosmology. Once large numbers of free electrons disappeared into neutral atoms, photons stopped scattering so frequently. Light could finally travel much more freely through the universe. This transition is called photon decoupling. The radiation released into free travel at around this period has been moving through space ever since. That ancient light is what we now observe as the cosmic microwave background. Originally, the radiation was far hotter and had much shorter wavelengths. But while it travelled, the universe expanded enormously. The expansion stretched the wavelengths of the photons until the radiation shifted into the microwave part of the electromagnetic spectrum. Today, its average temperature is only about 2.7 Kelvin above absolute zero. And although the cosmic microwave background has been travelling for almost 13.8 billion years, the regions from which it was emitted are not simply 13.8 billion light-years away. This is where the expansion of the universe produces one of the most surprising numbers in astronomy. The matter that emitted the cosmic microwave background is now roughly 45 to 46 billion light-years away from us in present-day distance terms. The photons did not travel across a static universe. While they were moving toward us, the space separating large-scale regions of the cosmos continued to expand. The light kept approaching Earth, but the distance between us and the matter that originally released it was also changing. So the journey lasted almost the entire age of the universe, while the present-day separation grew to tens of billions of light years. The cosmic microwave background has been studied in extraordinary detail. The National Aeronautics and Space Administration Cosmic Background Explorer mission provided some of the first precise measurements showing that this radiation has the spectrum expected from a hot early universe. It also detected tiny variations in temperature across the sky. Later, the Wilkinson Microwave Anisotropy Probe measured those variations with much greater precision. The European Space Agency Planck mission improved the picture further, creating exceptionally detailed maps of the cosmic microwave background. Those maps may look slightly mottled, with regions that are fractionally warmer or cooler than others. The differences are tiny, but they are enormously important. These small variations reflect slight differences in density in the early universe. Over billions of years, gravity amplified those differences. Slightly denser regions attracted more matter. Those concentrations eventually contributed to the formation of stars, galaxies, galaxy clusters, and the enormous cosmic web. In that sense, the faint patterns visible in the cosmic microwave background contain the earliest observable seeds of much of the structure surrounding us today. Measurements of this radiation also help cosmologists estimate major properties of the universe. They provide information about its age, its overall geometry, the amount of ordinary matter, the amount of dark matter, and other features of the standard cosmological model. And the distance involved makes almost every earlier reference point seem tiny. The Milky Way is roughly 100,000 light-years across. The regions associated with the cosmic microwave background are now around 450,000 Milky Way widths away in present-day distance terms. Andromeda lies roughly 2.5 million light-years from us. That once seemed enormous. But compared with a distance approaching 46 billion light-years, Andromeda is practically on the doorstep. Even 1 billion light-years, a distance that light would require 1 billion years to cross in static space, occupies only a small fraction of the radius of the observable universe. The scale has expanded so far that entire galaxy clusters, superclusters, and enormous sections of the cosmic web begin to shrink into comparatively local structures. But there is an important subtlety here. The cosmic microwave background is often described as though it forms a distant shell surrounding Earth. That description is useful, but it can also be misleading. There is no physical shell centered specifically upon us. We are not sitting at a special central point in the universe. Instead, we see the cosmic microwave background arriving from every direction because we are surrounded by regions whose ancient light has had enough time to reach us. An observer in a galaxy billions of light years away would also observe a cosmic microwave background surrounding them. Their observable surface would be centered upon their own location. The surface from which this ancient radiation appears to arrive is known as the surface of last scattering. It marks the regions from which photons were last scattered before beginning the long journey through a transparent universe toward us. And it does not represent the edge of existence. The fact that we cannot see electromagnetic radiation from earlier times does not mean there was nothing there. It means the universe before photon decoupling was opaque to freely travelling light. There was still matter, there was radiation, there were physical processes occurring. We simply cannot receive ordinary electromagnetic images directly from those earlier conditions. Other messengers, such as relic neutrinos or perhaps primordial gravitational waves, could in principle carry information from earlier epochs, although observing them presents much greater challenges. So the oldest light we can see is not the same thing as the farthest physical reality that exists. It is an observational boundary created by the history of the universe itself, and now the numbers have reached an extraordinary point. The universe is around 13.8 billion years old, yet some of the matter whose ancient light we observe today is now more than 40 billion light-years away. That seems impossible if we imagine the universe as a fixed stage through which light has simply been travelling. But the stage was never fixed. Space itself has been expanding throughout the journey, and understanding that expansion is what finally allows the true scale of the observable universe to come into view. At the largest scale we can meaningfully describe from our location, we arrive at the observable universe. The important word is observable. It does not mean the entire universe. It means the region from which information has had enough time to reach us since the universe began expanding. That distinction changes everything. The observable universe has a present-day radius of roughly 46.5 billion light-years. Its diameter is therefore approximately 93 billion light-years. Those numbers are not measurements of a solid boundary or a physical wall. They are estimates based on the standard cosmological model, the measured age of the universe, the expansion history of space, and the amounts of matter, dark matter, radiation and dark energy inferred from observation. Even so, 93 billion light-years gives us the largest practical scale of the universe we can presently discuss from Earth. And at first, the number appears impossible. The universe is around 13.8 billion years old. If nothing can travel faster than light, how can anything we observe now be more than 46 billion light-years away? The answer is that the light did not travel through a fixed amount of space. Space itself expanded during the journey. Imagine light beginning its journey toward the region that would eventually contain the Milky Way billions of years ago. The photon moves locally at the speed of light throughout its journey. But while it travels, the large-scale distance between widely separated regions of the universe changes. So the matter that emitted that ancient light can now be far more distant than 13.8 billion light-years, even though the light has been travelling for less than 13.8 billion years. This is one reason cosmologists use the concept of comoving distance. Comoving distance provides a way to describe the present-day separation between locations while accounting for the expansion of the universe. It effectively asks how far apart two widely separated regions would be measured on a cosmic map using the current scale of the universe. That is different from look-back time. Look-back time tells us how long ago the light was emitted. It is also different from simply taking the travel time of the light and multiplying it by the speed of light, because the geometry through which the photon travelled was changing. At small distances, these distinctions barely matter. At billions of light-years, they matter enormously. The approximate 46.5 billion light-year radius is closely related to something called the particle horizon. The particle horizon describes the maximum comoving distance from which signals could have reached us by the present age of the universe. It represents a limit created by the finite age of the cosmos and the way space has expanded. It should not be confused with the surface of last scattering. The surface of last scattering is the region from which the cosmic microwave background photons we observe today began travelling freely. The particle horizon lies conceptually farther back, because it concerns the greatest possible distance from which any causal influence could have reached us by now. There is also a cosmic event horizon, which is a different idea again. The cosmic event horizon concerns events occurring now whose signals will ever be able to reach us in the infinite future, given the continued expansion of the universe. Because cosmic expansion is accelerating, there are distant regions from which light emitted now may never reach us at all. The universe therefore contains several different horizons, each describing a different limit. And the numbers involved now make every previous reference point almost disappear. The Milky Way is roughly 100,000 light-years across. A diameter of 93 billion light-years is therefore equivalent to roughly 930,000 Milky Way widths. Nearly 1 million galaxies the width of the Milky Way could be placed side by side across the observable universe. Andromeda lies around 2.5 million light-years from us. The full observable diameter is roughly 37,000 times larger than the distance from Earth to Andromeda. The local group extends across roughly 10 million light-years. Around 9,000 local group-sized regions could fit across a distance of 93 billion light-years. At some point, comparisons like these begin to lose their usefulness. The numbers remain correct enough as rough magnitudes, but the human mind does not suddenly gain the ability to picture 93 billion light-years simply because it has been divided into 9,000 smaller impossible distances. This is where the ruler we introduced much closer to home becomes valuable one final time. Light crosses Earth in a fraction of a second. It travels from the Moon in a little over 1 second. It takes around 8 minutes and 20 seconds to travel from the Sun. It requires hours to cross the outer planetary system. It needs more than 4 years to arrive from Proxima Centauri. Tens of thousands of years are required to cross major portions of the Milky Way. Millions of years separate us from neighbouring galaxies. Billions of years are needed for light arriving from the distant universe. The same physical speed connects all of those scales. Only the amount of space changes. There is another subtle idea hidden inside the observable universe. It is centered on us only because we are the observer. That does not mean Earth occupies the center of the entire universe. Imagine an observer living in a galaxy billions of light-years away. That observer would also have an observable universe centered upon their own location. Their horizon would include some regions that overlap with ours, and potentially some regions that we cannot observe. Every observer possesses a cosmic horizon determined by location and cosmic history. So the observable universe is not one special sphere carved into reality around Earth. It is the portion of reality that can currently exchange information with us. What lies beyond our observable region is one of the largest unanswered questions in cosmology. The total universe may extend vastly farther than the region we can see. It could be finite and still be unimaginably larger than the observable universe. It could also be spatially infinite. Current observations do not allow us to decide conclusively between those possibilities. One important idea connected with this question is cosmic inflation. Cosmic inflation describes a proposed period of extremely rapid expansion in the very early universe. Physicist Alan Guth was among the major figures who developed the modern inflationary idea in the early 1980s, alongside important contributions from several other researchers. Inflation helps explain why widely separated regions of the observable universe have such similar large-scale properties, and why the geometry we observe appears extremely close to flat. If inflation occurred, the total universe could naturally be far larger than the region that has become observable to us. Measurements of the cosmic microwave background, including those made by the European Space Agency Planck mission, are consistent with the spatial geometry of the observable universe being very close to flat. But flat does not automatically mean infinite. A sufficiently large finite universe could also appear extremely close to flat across the limited region we can observe. So even here, at the greatest scale available to us, the numbers stop before reality necessarily does. We began with meters, then kilometers, then hundreds of thousands of kilometers, then astronomical units, then light years, then thousands of light years, millions, hundreds of millions, billions, and finally roughly 93 billion light years across the observable universe. Each new scale made the previous one look smaller. Earth became a point. The solar system became almost nothing. The nearest stars disappeared into the Milky Way. The Milky Way became one tiny galaxy among countless others. Even immense structures spanning hundreds of millions of light years became small pieces of the cosmic web. And after all of that, 93 billion light years still does not necessarily describe how large the universe is. It describes how much of it we can currently see. So how far away is everything in the universe? The answer depends almost entirely on what we are trying to reach. The Moon, which can look close enough to touch on a clear night, is on average around 384,000 kilometers away. That distance was large enough for Earth itself to become a useful measuring stick. Roughly 30 Earth diameters could fit into the space between us and the Moon. Then the Sun changed the scale. At roughly 150 million kilometers away, the Sun is almost 400 times farther from Earth than the Moon is. A distance that had seemed enormous suddenly became only a small fraction of another. By the time we reached the outer planets, billions of kilometers had become normal. Neptune lies around 4.5 billion kilometers from the Sun. Even light takes more than 4 hours to cross a distance of that scale. And then, the solar system itself began to disappear. Proxima Centauri is roughly 4.24 light-years away. In kilometers, that is around 40 trillion. At that point, kilometers had not become incorrect. They had simply become inconvenient. So the ruler changed. A light year allowed us to describe the distance light travels during an entire year, roughly 9.5 trillion kilometers, in a much more manageable way. But even that new ruler quickly became ordinary. Our nearby stellar neighborhood extends across tens and hundreds of light years. The Milky Way stretches roughly 100,000 light years across its main stellar disk. The solar system, which once occupied billions of kilometers and seemed unimaginably large, became almost invisible inside it. And then the Milky Way suffered exactly the same fate. Andromeda lies roughly 2.5 million light-years away. The local group extends across roughly 10 million light-years. The Virgo cluster lies more than 50 million light-years from us. Beyond that, the cosmic web contains filaments, walls and voids stretching across hundreds of millions of light-years. Eventually, an entire galaxy became little more than a point on the map. That may be the most revealing pattern of all. Nothing became physically smaller. Earth remained 12,700 kilometers wide. The Earth-Moon distance remained hundreds of thousands of kilometers. The solar system remained billions of kilometers across. The Milky Way remained roughly 100,000 light-years wide. Only the reference point changed. And every time the reference point expanded, something that had seemed impossibly large became unexpectedly small. There was one ruler that survived all of these changes. Light. Light can cross Earth in a fraction of a second. It travels from the Moon to Earth in roughly 1.3 seconds. It takes around 8 minutes and 20 seconds to reach us from the Sun. It needs hours to cross the outer planetary system. It requires more than 4 years to arrive from the nearest star. tens of thousands of years are needed to cross large portions of the Milky Way. Millions of years separate us from neighbouring galaxies. And when we observe the deepest regions of the universe, the light reaching our telescopes has been travelling for more than 10 billion years. The speed has not changed. The distance has. This is also why imagining the scale becomes so difficult. The problem is not that the numbers are mathematically incomprehensible. We can calculate them perfectly well. 1 million is 1,000 times 1,000. 1 billion is 1,000 million. 1 light year is roughly 9.5 trillion kilometres. The difficulty is that understanding a number is not the same as experiencing it. The human brain has never directly experienced 1 trillion kilometres. It has never watched light travel for 1 million years. It has never stood beside a gap between galaxies. Our intuition developed around rooms, landscapes, journeys and horizons. At cosmic scales, we are asking that intuition to operate far outside the environment that shaped it. Fortunately, our measurements do not depend upon imagination. The distances we have described are not simply guesses based on how small something looks in a telescope. Astronomy has built a chain of overlapping measurement techniques known as the cosmic distance ladder. The moon can be measured using laser ranging, with light sent toward reflectors on its surface and timed as it returns. Distances within the solar system can be determined using radar ranging, spacecraft tracking and precise orbital mechanics. Nearby stars can be measured through stellar parallax, using Earth's changing position around the Sun to detect tiny apparent shifts against more distant backgrounds. Farther away, Cepheid variable stars provide another rung. Their pulsation periods reveal information about their intrinsic luminosity, allowing astronomers to compare how bright they truly are with how faint they appear from Earth. At still greater distances, Type 1a supernovae provide extraordinarily bright markers whose luminosities can be calibrated. Beyond that, measurements of redshift and models of cosmic expansion allow astronomers to work across truly cosmological distances. No single technique stretches from Earth to the farthest observable regions. The strength of the system comes from overlap. One method calibrates another. Nearby measurements anchor more distant ones. The scale is assembled step by step, and eventually those steps take us to a number that is difficult even to say without losing its meaning. The observable universe is approximately 93 billion light-years across in present-day distance terms. Its radius is roughly 46.5 billion light-years. That does not mean light has spent 46.5 billion years travelling toward us. The universe itself is only around 13.8 billion years old. The larger present-day distance exists because space expanded while the light was travelling. Regions that emitted ancient radiation billions of years ago are now much farther from us than they were when that radiation began its journey. And 93 billion light-years is not necessarily the size of the entire universe. It is the scale of the region observable from our location. The observable universe is limited by the finite age of the cosmos, the finite speed at which information can travel, and the expansion history of space. Beyond our cosmic horizon there may be much more universe. Perhaps enormously more. The total universe could be finite while still being vastly larger than the portion we can observe. It could also be spatially infinite. Current observations do not allow us to determine conclusively which possibility describes the whole of reality. There may therefore be no final number available to answer how far everything extends. We can measure what lies within our observable region. We can calculate the distances to ancient galaxies. We can reconstruct the expansion of space. We can describe a visible cosmos around 93 billion light-years across. But beyond the horizon, observation eventually gives way to inference and possibility. And perhaps that is the strangest part of the entire scale. The same universe that contains distances measured in tens of billions of light-years also contains the few meters around you now. It contains the room you are resting in. It contains Earth, only 12,700 kilometers across. It contains the Moon, a little over 1 light-second away. It contains the Sun, 8 light-minutes from us. All of them occupy the same physical reality as galaxies whose light began travelling before Earth existed. So after moving outward through hundreds of thousands, millions, billions and trillions of kilometers, and then through light-years, millions of light-years, and finally billions of light-years, we can return to the place where we started. A small patch of Earth, a few familiar meters, and somewhere within an observable universe roughly 93 billion light-years across, that tiny distance is still real, still measurable, and still part of exactly the same universe.